Okay, so sections 1.1 to 1.4 are really the things that are on the summer skills packet. So we're starting up with section 1.5, and like I said, a lot of what we're going to talk about right now, you've already done either in Algebra 2 or Algebra 3. Domain and range. You can jot that down, and then I want you to have a conversation with your shoulder buddy really quickly, maybe 20, 30 seconds. What the heck do you remember about domain and range? Wait, no, hold on.
Domain and range is where X and Y lie within the concept of graph. I don't know but one of them is going to be on the possible X functions, one of them is going to be on the possible Y functions. That.
Okay, someone tell me, what is domain and range? Domain and range. Nicole? Yes?
Yes.
What did you guys say about domain and range?
You said like domain and like the X's and the range is the Y's.
Anybody have anything they want to add to X values, Y values? Anybody use any other words besides X and Y? Oh, Katie, what'd you use? That's the other one. Domain is inputs. Range is outputs. Anything else you want to add to domain and range, Mason?
They produce like things that aren't undefined. So like if it's 1/x, the domain can't be 0.
Oh, okay, yes. So you have to take into account sometimes like restrictions to the domain, or because of like the nature or shape of your graph, what would actually be included in the range. So these are the two phrases I've heard before. Some people say domain and range are the limits of the X values or the limits of the Y values. I've also heard, oh gosh, I forgot. Oh. Some people put just like all the possible X values, all the possible Y values. So then that kind of addresses what you're talking about, right? If it's 1/x, the domain is all the possible X values that give you an answer. So 0 doesn't work because we get something undefined. I love that. Thank you. Okay. Chelsea's hanging out in my room. Okay. We're going to talk about notation now. This is probably the newest thing that we're going to talk about today. Is anybody coming from Algebra 3? Okay, so you probably already know about interval notation, which would be really nice for you. Here's a picture of a graph. Okay, and I probably just took this from the textbook, but we're going to talk about domain and range of this particular function in our old notation, what we used to do in algebra. So our old notation, domain and range, we would use x's and y's and inequality signs. Greater than, less than, greater than equal to, less than equal to, that type of thing. So if we're looking at domain, like Nicole said, that's all the x's. So it seems that the first x that works is -1. And then we can go all the way to the right here. The last x, there's this point at 5, 2. What's special about that point? Or different about that point?
like not filled in, which means it's not inclusive.
Yes, it's not filled in, so it means it's not inclusive. So like it's a boundary, like that's the right side boundary, that's the last point, but that point doesn't actually work. So when I would write my domain, I'd say -1 is less than or equal to x, which is less than 5. Meaning 5 is not included in the domain because it's an open circle right there. It's not actually part of the graph. Okay, it's just the boundary of the graph. Okay, excellent. And then for range, we'll go back to what Nicole said, we'll be looking at our y values, so we're looking up and down on the graph, and we've got our lowest y value right here, the y value is -3, we've got our highest y value up here at 3, so that would be our range. So we would say something like -3 is less than or equal to y is less than or equal to 3. Okay, so that's old notation. Now, the new notation that we're going to use, and I want you to practice this on your homework tonight, switch over to interval notation. Okay, I want every time you do a quiz or a test for me and I ask domain and range, I'm going to want it in the new interval notation. We're going to use grouping symbols. The first grouping symbol we're going to use is a bracket. A bracket is like rectangular grouping symbol, so not a parenthesis. I've got a rectangle piece. And if you use brackets, you're saying the number is included. So brackets are included. If you think about the graph, that would mean that's a closed point right there, or a solid point. It's included in the domain. Or if you're thinking about our old notation, that would be anytime we use the inequality signs that have the or equals to. We would want to use a bracket. The other piece that we'll use in interval notation is a parenthesis, and a parenthesis means excluded. So those are things that are just less than, greater than, but they don't have the or equals to. Very tricky. Okay. So what we're going to do next is we're going to take that domain and range that we did for the function above, and we're going to change it into the interval notation. I think a lot of you will see, hey, this is less writing. This is awesome. Okay. So I'm going to take this domain that is -1 inclusive to -5, or to +5 exclusive. Okay. And so interval notation is going to look like this. The domain, bracket with -1, include -1, put a comma. Anytime you have a comma, then that means like everything in between. And 5 was where I stopped, so I'm going to have a parenthesis. So include -1, exclude 5. And then for range, when we look at the range, we've got or equals to on both of those. We're going to have brackets on both sides. We're going to go -3 to 3, inclusive on both sides. And there you have domain and range. Does anybody have any questions on this? Now, a big issue that will pop up is like most of our domains and ranges, if you think back to Algebra 2, Algebra 3, they didn't have two bounds. Maybe they had a lowest bound, and we would say like x is greater than 5. Well, what's the other side? We're going to be using infinities. So if it keeps going and it never stops, you would use positive infinity to the right and negative infinity to the left, up, down, okay, as needed. And maybe make a note somewhere in your notes about all real numbers. Haley will know this. All real numbers is just negative infinity to positive infinity. You always, with the infinities, use parentheses. because you can't include infinity because that's not really a thing, it just keeps going. Okay, so you always use parentheses with infinities. So on the next slide, I have another example of a function, and I'm going to show the next slide. I'm going to ask you in your small groups, so the same groups you did for summer packet, talk about what you think for domain and range. There is going to be an issue that we have not yet addressed, and so your group can maybe identify what is that issue that's coming into play, and then we'll come back together and we'll kind of talk about how we would form domain and range. But you can at least look at it and get some ideas going. Okay, so take a minute or two, look at the function, talk with your people, and remember, there is a problem. So if you can identify maybe what the problem is, that will kind of help you decide what your domain and range will be. Okay, so let's regroup. What is the big issue here? There's really like two domains. There's a section that's not included. Is that okay? Yeah, that's the graph, right? So you really have to set up almost like two domains, and then there's going to be a special symbol we put in between them. Okay? So if we were looking just at the left side, how would you write the left side? What's the furthest left it goes?
Infinity.
Negative infinity. So we would use parentheses negative infinity. And then what's the furthest right it goes? -1. Is that inclusive or exclusive? Inclusive, so we're going to use a bracket. Okay. Always write your two numbers in your symbols in the same order as the number line. So like negative infinity is left of -1 on our number line. Okay, so always write that in that order. If you have multiple domains or multiple ranges, we use a mathematical symbol that looks like a U. You guys know what that means? Union. Okay. So union, and it's just like the word and. Mathematicians, I always say, are kind of lazy people. We like to put everything into a symbol. So instead of writing that word, we'll just write U for union. And then we would do the same thing for the right. So what's the leftmost value on the right? 1. Use a bracket all the way to positive infinity. Always use parentheses with infinity because you cannot bound infinity. Okay. So there's your domain. Little issue with the gap. If you had 3 parts of a graph, you'd have 2 union signs in 3 different sections. And then what do you guys say for range? Just shout it out.
Brackets, 0, infinity, parentheses.
Thank you, Edith. Brackets, 0, infinity, of course, with parentheses. So 0, when you're thinking about range, instead of thinking like leftmost to rightmost, you're thinking up and down, so you're looking for your minimum to your maximum. Okay, and the lowest that that graph ever goes is at 0. Are we okay with this? Okay. Again, train yourself for your homework tonight. Write your intervals like this instead of our old notations. Okay, so my next thing that we want to discuss just real quickly, this is super easy, probably comes from Algebra 1 or before. I'm going to give you 2 questions to talk about in your small groups. Let me change my question. What is a function? And number 2, how can you tell if something's a function if you have a picture of its graph? What is a function? How can you tell something's a function when you have a picture of its graph? 20, 30 seconds. Go. What is a function?
Function relation that is length over a one intersection of another.
Because I'm on more than
Technically, one.
anything that
Well,
can be
it's one of those things where it's specified. So it needs to have like 1x. Well, 1x value not have more than 1.
I need one.
So like, and on this level, let's say this is 3, that means.
Okay.
Any line or shape presented on a graph. That that actually covers it.
What'd you say?
Any line or shape presented on a graph would be a function.
Any line or shape presented on a graph would be a function. Is that a function?
Pretty sure. You're not?
So some people say no. Why no? What is a function? What's important to be a function? It doesn't have to be a line, but that is a branch of functions, linear functions, absolutely. But think about last year, quadratic functions, exponential functions. I mean, all those things you studied in Algebra 2 are functions.
Should it not cross the y-axis like once or not once but twice, 0 more times?
I suppose that would be true, but you're kind of being very specific with your y-axis. Is this a function? No, but that doesn't fit your definition.
It can't like have a the vertical line.
So that's the answer to my second question, the vertical line test, which tells you you could pass a vertical line through the graph and it can only cross how many times? 1. So what does that mean about the definition of a function? I heard Mason. Mason, I know you said something. Can you share with us your definition of a function?
Every x value can only have one y.
Every x has only one y. Every input has only one output. And that can be tested visually by the vertical line test, because a vertical line is an x. It's an x value, and if that x value crosses multiple points, whether it be on the y-axis or somewhere else on the graph, then you have violated the definition of a function. So just really quickly, I'm going to show some pictures. Do these things pass the vertical line test? Is this a function? No, Lily is shaking her head in the back. Absolutely not. Is this a function?
Yes.
Yes. It's a polynomial. Okay. Is this a function? Nick says yes. Yeah, it's like the one we just looked at. Some people might take a second glance at that one because of the gap, but it's okay if not all the x's are included. Okay, it's just that every x can have only one y. They don't have to have a y. Okay. So the next thing we want to talk about is finding zeros. So again, I'm going to put you with your small groups and just brainstorm, what the heck does it mean when your math teacher asks you to find the zeros of something? So finding zeros, there's multiple ways to describe what finding zeros is. What does it mean to find a zero? Go ahead and have a quick chat with people around you.
That means points where four crosses the x-axis. Or the y-axis.
Just calculate out the base probability
Some x. If it's not across the point on that.
Okay. What is finding zeros?
Finding points where a function equals 0.
Finding points where a function equals 0. Any other? What are those points where the function equals 0?
crosses the x-axis.
Where it crosses the x-axis, what do you call that? What kind of intercepts? Yeah. You're finding the x-intercepts. if they're real, right? I guess we have that issue in Algebra 2 and Algebra 3. Some of the solutions turn out to be imaginary, so those are not x-intercepts on a graph because they don't show up in our real number system. But yeah, we're finding x-intercepts. We're finding the value when the function, like Ethan said, is really y equals 0. So when y equals 0, you're sitting on the x-axis, wherever that may be. Here's an example, and I'm not going to spend a whole lot of time on this just because we've got a lot to do today and I'm going to get through it all. This is similar to questions that maybe you saw on your summer packet. What method would you use to find the zeros of this function? How could you solve? You could do quadratic formula, okay?
You could factor it.
Or you could factor it. Okay, so quadratic formula or factor. And this one does factor. Okay, if you want to try it later, you can. Just note that, like, going back to sort of Ethan's definition there, we're saying the function equals 0, so we'd be saying 0 equals 3x squared plus 22x minus 16. And then it's however you're going to solve for the x's. You know from Algebra 2, if you have x squared and x, you're kind of on a train of factoring or quadratic formula, and that's all you got. You could complete the square, but on this one with an a value of 3, I wouldn't even go there. So we divide by 3 first. Okay. I am also going to show you how to find zeros on your graphing calculators, but I'm going to skip that slide for now. We'll see if I finish with enough time to show you before the end of class, or I'll show you at the beginning of class tomorrow. It's pretty quick. But there's one tool that you can use your graphing calculators for. So I'll come back to this one. Although I will include this on the online notes that I post. I always post like a PDF of my notes on my website. And so if you want to read what's behind the screen there and you want to just practice it at home, you certainly can. But the other thing I want to talk about is also intervals of increasing, decreasing, or constant parts of your function. So when you look at that graph, can you tell where it's increasing and where it's decreasing and where it might be constant? Yeah, I think that's pretty clear, right? I'll go ahead and label. If I look for all the increasing sections, I'm increasing here, so I'll put an I. I'm also increasing here. Okay. And then if I look for decreasing sections, I've got a decreasing function and a decreasing function there. And on this one, it doesn't appear that I have any places where I'm constant. Okay. And so the only thing I want to mention about increasing, decreasing, and constant for your homework assignment is if you're writing those intervals, you're going to use the new notation, the interval notation. So that'll give you an extra chance to practice. And this one, this board here, we can't really see, but I'll put little. Okay, there's some tick marks there to kind of frame this. So when is it increasing for all x's from -3 to 0? And when you're doing these, use parentheses. Okay, because at -3, it's not really increasing or decreasing. That's its turning point. At 0, it's not really increasing or decreasing. That's a turning point. Okay. So I would do that, and then I would do, this is from 3 to infinity for the other piece of increasing, that blue piece over there. And then I would do the same thing for the decreasing sections. First decreasing -infinity to -3, and then 0 to +3. And again, on these, I choose to use parentheses because at those points, it's hard to say if it belongs with the increasing or decreasing. It's really just turning there. Are we okay with that? So that gets into the very last piece. How would you describe those points that we didn't include anywhere? What words might you use to describe these points? Turning points? Yeah, there like a vertex, especially here.
Mhm.
In relation to the two sides of the graph right here, this point is the highest point. So you might call it a maximum. In relation to the graph right here, this is the lowest point, so you might call it a minimum. And same for this point right here. So that gets us into the very last piece of what we want to talk about today, which are relative minima and maxima. Relative minima and maxima are the points where a function switches from increasing to decreasing. Notice that there is that word in front of them that says relative, and that's a pretty important one because it means it's relative to the graph just right around it, right? Like when I pointed out, like right here in this little group of points, this is the lowest point. But if I flip back to that slide and I show you that one more time, is this actually the minimum of the function? No, because there's an actual real minimum over here. We would call this one right here a global minimum. Global minimum. Because for the entire function, it is the lowest point. Okay? And then this would just be a relative minima relative to the graph around it. And then same for this. We're calling this a maximum or a relative maximum. But it's not really the maximum because it looks or appears that it's going towards positive infinity on both sides. So it's not even the maximum of the function. Okay, so you got to kind of be aware of that when you're looking at relative minima and maxima. Okay. Think about all the things, and I'll show you min and max on the calculator tomorrow. Think about all the things that we've talked about today that, like, if you struggled on that warm-up, that you could add to that tomorrow if I show you the same function. Okay? You do not have to write all these problems down before you start. You do not have to write all these problems down because you get problems here. Yes. So this is what I referred to earlier as the gold sheet, and this is like your master sheet for all of Chapter 1. If you're going to be gone a day, if you have a sporting event or some other reason to be gone, you know exactly what we're doing in class. You know what your assignment is. Notice that some of the problems are bolded and underlined. If you read at the bottom, it says those are required. Okay. So you should do those required problems and then do the others if you have the time. Okay. And tomorrow we'll go over a couple of quick things in the notes, and then you will have summer skills quizzes.